Dinesh, Manocha, University of Maryland, and I want to welcome everybody to ICRA. Good to see everybody in person. I really miss ICRA I've been attending for almost 20, 30 years now. And this is a workshop on construction, and we already gave a lot of motivation of why economic impact is so high and where things go. So I'm going to talk about some of the project I've been working with Baidu Research with Liangjun Jiang, who's sitting right there. This is a more than 3-year-old project where we actually developed one of the first autonomous excavation system. Now, construction has a lot of modules, a lot of components there, right? So there are a lot of technologies needed. We just saw a nice demo of a robot working. So one important part is autonomous system, this excavation, and this actually paper appeared in Science Robotics last summer, was it? So just to give you a feeling of where we are, it's very hard to get the latest number. We just heard recent 4% GDP in USA, 11% GDP worldwide. So excavation is a big chunk of construction. It's not the only thing, but it's a big chunk. Here's some outdated numbers, but way back in even 4 years ago, it was about global market was $44 billion. I don't know the latest numbers, but my conjecture is the way construction industry is going, these numbers are pretty outdated. And China, which has seen a lot of construction boom, even in 2018, there were 1.6 million excavators. And they're still selling a lot more excavators thing. The number of excavators sold and the number of excavators used. So this equipment lasts a long time. And all the challenges you heard about construction, I don't know how much you can see, this slide is a little bit fuzzy here, but there are a lot of accidents that occur. There are a lot of dangerous conditions that occur. There's a lot of fatigue. So all the reason why we need automation in construction are really applicable here. You'll see even excavator we are deployed, they're working for waste material with toxic kind of material. So we definitely want to avoid that and literally, make sure that things work well. So the notion of excavator is not new. We were not the first one to do it. There were at least previous systems. One of the earliest systems was at Carnegie Mellon at NRAC way back in late 90s. You can see autonomous loading system. There's some really work that even at ETH. There's a lot of work on earth moving equipment. Moving stuff around it's not a novel idea. It has been around for a while. We go from there. And there's a lot of work happening there. I would say there's a lot of boosts coming up in the last decade because a lot of investment has gone into autonomous driving. If you see some recent media article, the venture companies or the big firms have spent close to $15 billion, So as part of autonomous driving industry, there have been a lot of developments in better LiDARs, better camera, and of course, a lot of investment in perception and planning for navigation. So a lot of the results in a lot of the technology invested in autonomous driving, we can leverage it here and do well. So this was a system that we put together. It's a large team at Baidu Research led by Liangjun himself. But you can see, you take excavator and all kind of sensing comes in. There's a camera, there's a LiDAR, there's a pressure sensor, inclination sensors. And you have to make sure, when they're on heavy excavators, it's reliable. There's a lot of vibration, there's a lot of force being applied, and you go around. Demonstrate, as I said, the idea of excavation is not new, but the real challenge in the take-home message I want to give from this talk is that the real challenge in this work is actually an integration. There's a lot of work on perception, planning, control. As an academics, I myself write a lot of papers on that, but what you don't realize is that how do you make planning, perception, and control work together? And how do you reach a level of reliability? There were like hundreds and hundreds of engineering challenges solved, which is, I can't talk about it in 15 minutes, and we could not talk on the paper, but literally what this was able to demonstrate, which I hope was a big thing, that the efficiency was close to human operation. About 80, 90%, 95% is getting better and better of humans. Robustness, it's operating. You saw a big, small video there, but this actually have been deployed in a site where it actually worked 24-hour nonstop. So this is really 24 hours, not thing. And this particular user has used it for more than 8,500 hours. So we hope this metric that can work for 24 hours nonstop, achieve close to human level efficiency. Humans are really good operator, how you do the thing and do that and reach that goal. So this is really to deploy that it's no longer a proof of the concept, it's really being used and people are really literally benefiting from it day to day. So what are the components? Any of these autonomous systems, just like autonomous driving, has, as I said, 3 big high level: perception, planning, control. This pipeline is not new, it's been around. Now, perception got a big boost, computer vision. Last 10 years, deep learning has totally revolutionized it. And secondly, the number of sensors, right? The number of LiDARs and the cameras are coming around. So perception came a big level here. And you can see the multiple sensors here. In planning, we always talk about break down into high level and low level planning. High level is task level planning. You give high level tasks, like operator says, I want to deal with loading. I want to deal with rock removal. I deal with trench shrinking or water deposit recycle. This high level task. You take the high level task and break it down into what we call in classical robotic motion planning. It'll be a series of motion planning problems, things like digging, rotating, dumping, sweeping. So you can imagine building a low-level library of motion planning modules and a high-level task library there. And of course, control. You have to have this hydraulic motors or other mechanical parts. They have to work at really high thing. And of course, there were lots of challenges. You use as much open source software possible, but at the same time, a lot of software come together. So this is again, I want to emphasize the level integration was at least definitely non-trivial. So this is the challenge we all face any automation system. This is what every vendor of autonomous driving system deals with it. They've got a large team to work on and put together. Let me give you examples of what kind of perception challenges we deal with. So it's a perception pipeline. Now, when you're in a construction site, you're dealing with a lot of dust and rocks flying around. So if you see, from here, I'm seeing like even this, some of this projector looks hazy, but in construction site, the scene is always full of hazy and dust. So we had to cover the new pipeline for what is called de-dusting, for lack of a better word. You see lots of papers in computer vision, robotics. I'm sure it covered lots of papers on all kind of perception, but there was not just much work on de-dusting. Not many people dealing with de-dusting. So we had to really gather our own data, train our network to get it right. What kind of material is it? Is it hard soil? Is it rock? Comes up there. A semantic segmentation. You'll see that, that this is where the rock is, this is where the water is, this is where the grass is, leave it around. And an instance simulation. And finally, for the actual operation where you pick up rocks, you have to really figure out the 6-stop pose estimation, what pose you take. And this will become more clear in the pipeline. So this is just, I won't go into the details of that. It's in the paper, just a network to show the de-dusting pipeline, dehazing or de-dusting. You give an input image and you have this whole pipeline of network, does it right. So let me just show you how this works. Again, the details of network and the paper, I'll spare the details of you for lack of time. But literally, this is how the input looks like. What you see, of course, it looks even worse on the projector than when I was looking on my laptop. So you can barely see anything. So let me see if can we turn the lights off? Maybe slightly, the projector is not very focused, I think. So we need a better focusing projection, deep learning in the projector right here, right? So can we turn the lights off by any chance? Anybody with the luck on that? Okay, so this is it. This is like what I call the fuzzy version. And you can see a little bit sharper with de-dusting, and same thing on the right-hand side. So this itself was, one of the first perception module. When we started working on this project 3 years ago, we did not expect that. So this is one of the biggest challenges that come in the process, that you're dealing with lots of fuzzy, a lot of flying dust, and how do you deal with it? So this is kind of, again, examples of, you'll see at the top are the dusty images, and on the bottom are the results of the network, like de-dusting, for lack of a better word, or just better focus. So you can do better recognition on these kinds of things. Running segmentation on the top row would not work as well as segmentation on the bottom row right here. And of course, to get the perception work right, we have to build our own data set, because deep learning only works well if you have a good labeled data. And in this case, we generate data sets. In this case, we took into account 8 classes. You can see the 8 classes from dry soil, wet soil, again, probably you can enter all the way to titanium and mixture. This is, of course, not exclusive. I'm sure you could have construction sites with more than 8 materials, but we can train it accordingly. This can definitely handle up there. But to get a real good data set to make it work well, we took almost about 6,700 images for training and 800 for testing. The typical, breakdown in deep learning methods of 80-20 or 90-10 kind of testing and training, and build a database. And literally, we found out that using attention strategy with a deep encoding network worked well. So we got pretty good results once the database was there, network was trained well. And I said the other part was segmentation, this thing. And the last but not the least, you got big stones, you got big items to lift. And how do you deal with them? You figure out the pose of the stone. If you see a large rock or large stone, how do you go and do it? Now, humans can figure out how to, put your manipulator at the head at the end. But in this case, everything has been automatically. So this is just an example of see how rock removal works. You detect and you'll see how the excavator comes and literally lifts it up. This is automatically done to figure out the whole pose or what angle it should come, what force it should come down with and lift it up. So this is kind of operation. On the left was the actual simulation, the actual excavator. On the right-hand side, you see the screen capture from the actual system. So this is it. This is, again, of course, other thing, as we heard this morning, like construction site. When you're construction site, things changes every half an hour, right? It's 24/7 operation, digging going around. So if you're running an excavator for 24 hours, doing a big job of waste disposal, the terrain is changing, very frequently. So you have to have what is called a real-time terrain reconstruction, which is, again, typically in vision people, they don't do that. But construction has this challenge that the site at which you're operating, I want to emphasize that mentioned by the morning speaker that happens very frequently. So you need real-time capabilities for doing this computation. This high-level task planning and low-level motion planning. So the hierarchical planner we put together. What you see on the right-hand side, we took a lot of components together. These are pretty good, well-known technique like MSRP based on material removal and BSMP, R planner, base planner. So this whole planner was put together by taking a lot of technology which robotics communities developed for the last 40 years and put them together here. Especially for the low-level planning, we use optimization-based planning. This has been around. There was earlier work on CHOMP and STOMP. My own group at UNC did a lot of work on ITOMP. There are a whole bunch of planners, optimization. And literally, we specialize it here to see what comes up here. Optimization cost depends on you want to make sure that it's a joint limit, take into account collision count, bucket flat, and final goal state cost. And you make sure that there's no collision. So you set up an optimization function, follow the favored gradient descent method. In this case, we use what is called stochastic optimization. And of course, optimization method is susceptible to how good initial guess you take. So if initial trajectory is good, you basically get good convergence. And in this case, we know the task we're doing, we're able to optimize that. The good thing is, it's pretty real time. It's at least it's getting fast. It was not the biggest bottleneck, though of course you can always make it faster out here. So this is the thing, but this is exactly you'll see. So on the left, you see the caterpillar with a human operating. You can see the slow motion, how it opens up the head and literally dig it up. And on the right-hand side is our voice system working in real time automatically. So getting close to human efficiency, of course, humans are humans, automation system getting there. But as I said, overall, we got pretty close to human efficiency, and our goal is that as you deploy it more, gets better. It'll be good to compare the nodes in 5 years. Could we do better than human, right? Especially if you're operating for 8 hours. This is going to be a nice automation versus human performance, though we don't have to get into this kind of a race, but we're getting pretty close to it already. Now, here are some trajectory controllers. So in the controller, the big challenge was there are different kind of excavators, light and heavy excavators. You don't worry about this thing. So, the motion control in hydraulic actuator was a very big challenge. Again, I will not go into details of that, but literally there was a lot of effort done and to make sure that the controller can follow the planned trajectory in about, close to 10 centimeter accuracy. So this is a pretty big scale, and getting this kind of level of accuracy on this kind of a system was non-trivial. And again, I want to emphasize again, I'm going over the perception planning, both task level planning and motion planning quite quickly, and controller. But I want to again re-emphasize within each of them, there were lots and lots of problems. This is a very large team of people working, some in the research lab, some on site to make it work. So this was definitely good result at the end, but there was a lot of effort to make it work well. So let me just show you how the system works, because the proof is there. But before I get into that, we've done some extension of this work. Recently, one of the students, Tiandre Guan, he has been working on it. The paper going to appear in RSS at the end of next month in New York. So this was that particular excavator system we developed and presented in Science Robotics was sitting in an area doing it. But we also want to walk in the terrain. So how do you do terrain analysis? Like, is the terrain traversable? There could be water, there could be rain, there could be some spaces the excavator not good for go, and the navigation. So we went to the next level that you also do terrain analysis in a larger area and do with mapping and navigation and go with that. So this is a system called TNS, as I said, presented next month. I will, again, the paper's on the web, but you can see it's a real-time traversability estimation. Again, real-time because terrain is changing. The construction site is changing. You can't do it one offline. And real-time brings a lot of challenge there for an estimation system. So planning, mapping the area, planning and navigation. They developed new traversability methods, complex terrain. Terrain traversability is a pretty well-studied problem in vision, but We had to really customize new methods for these kind of applications. They were not done in this environments. And again, integrate this with planning and control. And of course, there's also a complex work set terrain data set. The data set we had to do, again, just like we did the previous data set for dedusting. So Tiandra did this work on collecting terrain data set collection, which again has about, it's on the web now, hopefully. You got 30 minutes of video with a human operating and close to about 669 RGB images, to come back. Now, you might see this is not, 669 is not considered a big data set in computer vision nowadays, but getting data sets from real sites is not easy. You have to go there and collect and label it. And again, you can see you have data sets which are flat, shown in kind of green, yellow is bumpy, to all the way to water is red, rock, obstacle, excavator. So these are like, you can see we have about 7 classifications here. Because I think, stop if I'm adding it up, but this is what we found in our system, and that's what deployed it right here, which is helpful. Here's the perception pipeline of the whole doing terrain traversability and again segmentation. And because of lack of time, I would just not details into that, but the papers on the web. And if you attend RSS, you can hear Tiandra's talk there. And this is the planning stuff. The planner we do actually ultimately was the perception module is right here, traversably map your compute using deep learning network. And then they go to tracking, control, navigation, how the system come together. So this on the left is again the perception part, traversability. On the right-hand part, as you do the traversability map computation, you got to run the module in real time. So again, you'll see this is like the RGB images, semantic segmentation. You also get the color point cloud, a traversability map. They all come together. Again, my apologies for going over the stuff very quickly, but I want to give you where things are going. So this is trying to show how it's been deployed. So literally, I want to spend last couple of minutes on learning what makes it work and what challenges come up. Real challenge comes up, as I said, doing it in your lab is one thing, but this is going to remote sites. And a lot of the excavator use, they're using construction sites. There's a lot of interest in using them for mining applications. It's getting it. There's a lot of work on mining on developing autonomous vehicles, which transport the material around, but this is there. So challenge here was, challenging in different kind of weather and terrain condition. It could be, cloudy day or sunny day. The perception methods might change, right? This is it. So you see dry soil, wet soil, big rock capture, bottom left rainy weather, small rock excavation, and wet soil. So these are at least some scenario we tested it, and I'm sure this is not exhaustive. We go from here. So this was a video shown. This was also shown this morning in the first presenter. You can see it operating right here, and this was totally automatic. There's no teleoperation here. This is literally working, loading, and you can see it's picking, and also figure out the way the truck poses, go gather the dust, figure out the pose of truck, and go and dump the dust or sand. That's what literally happens. So all these components of perception, planning, control come together quite well. And then the last part, the TNS part, navigation, you'll see right here, So this is, so literally, this is a control command, and this is a view from the excavator. It's doing autonomous navigation. And again, you can see this is not the most friendly place to navigate. We all see autonomous driving. We see beautiful video from Waymo Cruise. Those are beautifully nice maps, San Francisco road. Life is always flat and good. This is not your friendly place to navigate, right? Most of us don't navigate excavators here. So this is there. But of course, as you do initial testing, we have a safety protocol, and we're testing right here. But let me show this to you. And this is using the TNS system, terrain traversability and mapping, and going around with the hybrid planning right here. So this is it. One of the application was actually deployment in called waste disposal recycling. It's a waste site using AES, and literally it's an industrial waste cycle, which consists of toxic material and dusty. So this was literally a site which is not safe for humans, human operator text website. And this is where we deployed and tested for 24 hours. So this is, I'll show you the video right here. So this is literally, toxic material. You see all the material right there on this side. And on the right-hand side, you put a camera where the driver would have sit. It's like the driver's view. So this is like they install a camera outside. You see the AES system operating and day and night. And this is a camera inside where the human operator would sit and how it's being deployed. So this is literally happening for 24 hours. And you can see, again, waste site disposal. This is where different components come up here, and running time, efficiency. And I said, we really measure it compared to some humans, I was getting close to 95 to 100% efficiency. It's getting close to pretty human operation. And here's a final video which literally shows you that it worked for 24 hours. So we had cameras here, see on the midnight, operating here at 12 o'clock. This is around 6 a.m. in the morning, around noon, and around evening. This literally went on for 24 hours, and you can see also, how the dust and all the toxic material got changed because it was operating and doing quite well. So last but not the least was, as you do into working into clutter rigid object excavation, a lot of times you deal into excavation, which are very tough sites. So this is by no way a complete piece of work. There are lots of places excavator use, especially in mining. We're coming in more and more cases being deployed, comes up here. And one thing we also trying to work on is autonomous wheel loader. That's the next system. So this is just a simulation of that, Ultimately, what people want to see is that we got the basic excavation, we got the traversability mapping and navigation system, but you literally want to go and load this website. So this autonomous wheel loader here, come back here, and this is just in a simulation. You'll see how it goes around. There's definitely been a lot of deployment. We're hearing from a lot of our partners and collaborators. There's a lot of deployment of vehicles, autonomous trucks, millions of miles to move things around. But you can imagine, this autonomous trucks and autonomous excavation together and doing large amount of jobs, and especially in the mining industry and some kind of construction industry where it has a huge potential right here. So I think I'm beyond my time. Let me just, to conclude, we hope we demonstrate to you, this was a big team effort on building autonomous excavation system. We could show close to 24-hour non-stop operation, but a lot of effort went into reaching the 24-hour reliability, been deployed for 8,500 hours. And as I said, this is just a start. There's just so many challenges. We can have lots of team, lot of people work on a lot of PhD problems right here. They're different kind of excavators, right? They're lightweight, heavyweight, wheel loaders, cranes, shovels. We haven't done all of them. We've just done some of them. You have taken into account the dynamics. You got to wire them, comes up here. There are more challenging situations. A lot of the mining industry people deal with environment, which is not a nice, beautiful, sunny day in Philadelphia. It's a very challenging environment. So how do you really deploy it and reach it there? And of course, someday, we're going to have a lot of excavators. And one of the challenges that is coming up in industry is economic, that there are lots of excavators being deployed. They're pretty heavy equipment, the big ones, right? Now, people come and ask us, can you automate it, right? You can't just take your own car, your own Camry at home and make it autonomous, even if autonomous car will solve problem. So these excavators have a lifetime. Can we automate it? That's a whole new challenge out there. But meanwhile, we hope that we have shown this is possible, it's being deployed, and hopefully this will only get better. Thank you very much. Do you have time for any questions?